So welcome to the last part of Lecture 8. In this part, I kind of actually want to spend some time doing a little bit more of a complicated example that uses some calculus. So I'm going to give you a lot of the details and just so you can see a more worked out example. And it's similar to some of the things that you might find in a textbook if you're trying some of the sample problems. So here we're looking at a U, which is going to contain all the polynomials of degree 4 or less, such that when I integrate that polynomial from the interval -1 to 1, I get the value of 0. And what I want to do is I want to find a basis for U. So one thing you might want to try to first convince yourself is that this is actually a subspace. And you know how to do that based upon what we've talked about in a couple lectures ago. Okay, so how would you want to tackle such a thing? Well, the first thing that you want to notice is that the dimension of U is not equal to the dimension of the whole space. Okay, so P4R is all the polynomials of degree 4 or less, and that's a 5-dimensional space. And what we notice is that there's at least one thing that's not in U. Okay, and in particular, the polynomial 1 is not in U. And why is that? Well, here's some basic first year calculus. If I integrate 1 from the interval of -1 to 1, I get x going from 1 to -1, and I plug it in and I get 2, which gives me 0. So I know for sure that 1 is not in U, and if the dimension of U was 5, then these two spaces would have to be the same, which is false. Okay, so we know that the dimension of U cannot be 5. Okay, so hopefully that part is clear, that U cannot be everything, right? So if the dimension of U is 5, these two spaces would be the same. So that part should be clear, and you should know that from calculus that not every polynomial would have this property right here. Okay, so now the next part here kind of comes out of nowhere, and that's just because I did a lot of scratch work before I presented this. But I found a whole bunch of polynomials that actually are in U. So here, using some basic calculus, the polynomial x integrated from -1 to 1, if we look at that, we get this is equal to x squared over 2. And when I look at it from 1 to -1, here I get 1/2 minus 1, 2, oops, sorry, let me fix that here. I get 1 squared over 2 minus -1 squared over 2, which will give me 0. Okay, so x is definitely going to be in my set U. What about the polynomial 1/3 minus x squared? Well, if I do all the work, right, so this is 1/3 x minus x cubed over 3, and I plug in 1 to -1. If you do all the work here, you'll find that this guy is also equal to 0. If I do x cubed, right, so this is equal to x4 to the 4, 1 to -1, and you check my calculus, this will be equal to 0. And finally, if I integrate 1/5 minus x4, what I get here is 1/5 x minus x5 to the 5, and I'm integrating from 1 to the -1. And maybe just so you can convince yourself, I'll write out some more details. So I get 1/5 minus 1/5, and then I get on this side, I get minus 1/5, and then I get minus 1 to the 5th or 5th. Right, so over here I get minus 1/5 minus 1/5, so it gives me 0. Okay, so I have a whole bunch of polynomials that I know that are inside of U. I have x, 1/3 minus x squared, x cubed, and minus 1/5 minus x4 are in U. Now this part might be totally obvious to you, but these elements are all linearly independent. Okay, so let me write this down. These elements are linearly independent in U. And one way that I can see this is that they all have different degrees. They all have different degrees. So what I mean by that, if you were to try to find a linear combinations of this that equals 0, well, you would be forced to take each of the coefficients that gave you 0 to be 0. So it means that these polynomials are all linearly independent. And if you're not convinced of that, you should, take out some paper and pen and check that I'm right here, that these elements are linearly independent. Okay, so what do we have then? Let's think about what we have. Is 4 is equal to the dimension of this space, right? Because x1, 1/3 minus x squared, x cubed, and 1/5 minus x4. These are 4 linearly independent things. We're taking the span, so this is our basis. So we have that 4 is the dimension of this span. But what else do we know? Well, the span of these things here is inside of U, right? So we know that this set here is inside of U, so it's a subspace, so the dimension of U has to be greater than or equal to this space right here, because this is a subspace. And what we proved or mentioned at the very beginning of this example was the dimension of U couldn't be 5, so it has to be less than or equal to 4. So this is less than or equal to, oops, let me use a different color. This is less than or equal to 4. So what we have is that the dimension of the span of x up to 1/5 minus x4 is equal to the dimension of U, which is equal to 4. But now we have a subspace which has the same dimension as the space U here. So this implies that span of x up to 1, maybe I'll write out all the details. The span of x 1/3 minus x squared, x cubed, and 1/5 minus x4 is actually equal to U. And these guys are linearly independent, and they're spanning set. So as a consequence here, that this is a basis for the subspace U. Okay, so this is a complicated example because you have to kind of use a bunch of different results. And one thing that you may be wondering is like, where did I pull these guys out? Well, I kind of reverse engineered it. I knew that if I can find elements of different degrees inside of U, they would be linearly independent. So I worked backwards and I tried to find elements of different degrees that satisfied the property that they were in U. Anyway, that gives you kind of a detailed example, something a bit more complicated that you can do with some of the things that you've learned so far. Okay, so that is it for lecture 8 on dimension. So the key ideas here are, what is the dimension of a vector space? And, oh, here, I'll make myself pop back. So key ideas are the dimension of the vector space, and then the relationship between dimension, span, and linear independence. So if you know 2 of them, you actually get the third one for free. So you want to think of these 3 things as being linked. You know 2 of them, you know 3 of them. So I hope you enjoyed this lecture on dimension. There's kind of lots of interesting things here, and I will see you in lecture 9. Have a great day.